we're going to take a look at the effects of temperature and pressure on solubility of solids and gases. To begin with, let's take a look at solids. Light pencil, light pencil. What you can see here is there's a plot of temperature, increasing temperature, and the solubility in grams of solute per 100 grams of water. And you can see the general trend is that as temperature increases, most of these guys, the solubility also increases. All right, these are all increasing. Sodium chloride increases, but just a little bit. So that's kind of interesting. So at 100 degrees Celsius, right, boiling water, you can dissolve about 40 grams per 100 grams of water, and only about, 37 grams per 100 grams at 0 degrees Celsius. So it doesn't change very much its solubility. Some compounds, sulfur dioxide, HCl, these guys apparently are less soluble at higher temperatures. So it can depend. Whether or not something, as it dissolves, gives off heat is sort of related. No, let's talk about that after. Let's talk about fractional crystallization. It's more pertinent. So you can separate mixtures based on their solubility. We've separated things. Have we separated anything in lab? Not really. I guess we could filter stuff. But let's take a look. So here we have a system with 100 grams of potassium nitrate and sodium chloride. Okay, so let's heat this system up to 70 degrees Celsius. Okay, so it's set. Oh, no, I don't want that. I don't need that. Hold on. I only need about, let's go to 60 degrees Celsius. So at 60 degrees Celsius, how much KNO3 can dissolve? 110 degrees. So if I have 110 grams. So if I have 100 grams, all of it's dissolved. So at 70 degrees Celsius, 100 grams of KNO3 is dissolved, right? And how much of the sodium chloride is dissolved? We're just going to call this 40. All right, so 40 grams is dissolved, which means 60 grams is not dissolved. It's solid. This is my aqueous. All right, so in my beaker, I'm going to have, all right, a little pile of sodium chloride in the bottom there. So what I'm going to do is I'm going to filter that, and I've just removed it. So now what I have is, in my beaker, I've got a solution that has 40 grams of sodium chloride dissolved in it and 100 grams of potassium nitrate. And that's it. Then what I'm going to do is I'm going to cool this down to 0 degrees Celsius. Now let's look at the solubility. So at 0 degrees Celsius, pretty close to 40, we'll call it 38 grams of sodium chloride is still dissolved, right? But what happens to my potassium nitrate? Now only, call it 12 grams is dissolved, which means that how much has fallen out of my original 100. So now we have 88 grams of KNO3 in the bottom now. So instead of being like this, so now we've got 88 grams here, and we've got 12 grams and 38 grams in solution. If I filtered this off, though, filter this, now I've collected most of my potassium nitrate. So by filling with the temperature and then filtering, we're able to separate those guys into purer fractions. That's called fractional crystallization. If you think about dissolving things, we've talked about heats of vaporization. We've talked about heats of fusion. Right, this is the energy required to vaporize a mole of a substance. This is the energy associated with freezing a mole of something or melting it. Heat of solution is the heat, right, the energy associated with dissolving something in water. So if I take lithium chloride and dissolve it in water, delta H for that reaction is negative, which means exothermic, right? That means it'll give off heat. The beaker will start to feel warm in my hand. What about sodium chloride, though? As it dissolves, that's a positive value. That's endothermic. Thin pencil. And that means it's going to cool off, right? It's going to take heat out of the system, or out of the surroundings, me, and it'll feel like it's getting cold. So solution, dissolving things in water can be either exothermic or endothermic, depending on the energies associated. Which of these, though, would you want to use for a cold pack? So what you do is you put a salt in here, right? You break open a little packet so it sees water, and then if it's endothermic, it'll cool off. If it's an exothermic process, it'll warm up. So who would be best for the endothermic side? Who's most endothermic? Looks like KBR. So I'd put some potassium bromide in there, right? When it saw water, it would start to cool off and soothe my aching joints. What would I use in my hot side? I'd want the most exothermic thing. Probably not the best choice, but we'll use this guy, potassium hydroxide, right? This is the most exothermic. As this breaks open, it's going to heat up, right? I can stick it in my mittens to keep my hands warm in the cold. Classic Canadian tradition. Except Canadians' hands don't get cold. We just don't worry about it. One problem with using potassium hydroxide is it's a strong base. So if this little packet broke open inside my mitten, it'd be kind of tragic. All right, so that's solubility and temperature with solids. Gases are different. So as temperature increases, what is happening to the solubility now? It's decreasing. Gases are less soluble at higher temperatures. And if you think about that, it makes sense. So here we have, this is cold Coke, I guess, or Pepsi. And this is warm Coke / Pepsi, soda. Let's call it soda. And so what you have are the molecules of gas, right? CO2 gas dissolved in here, which makes it fizzy and delicious, moving around in there. At lower temperatures, they move kind of slowly, right? At higher temperatures, they're moving faster, right? And so they're more easily able to escape. And this is why at higher temperatures, gases are less soluble. So it brings up the question, should you keep your Coke in the fridge, 4 degrees Celsius, or on the counter, 25 degrees Celsius, if you want it to stay fizzy longer? Obviously, you want to keep it cold, right? All right. One other thing we can consider with the solubility of gases is pressure. So Henry, this guy, he studied the effects of pressure on top of a system, right, and the solubility. And what he saw was that if you doubled the pressure, so I went from 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Nice. We doubled the pressure. The solubility also doubles. So we went from 4 molecules, 1, 2, 3, 4, 5, 6, 7, 8, to 8 molecules. And this sort of makes sense, right? If you have more gaseous molecules trying to push in there, it makes sense that they would be more dissolved in there. All right, his formula can be written like this. The concentration, or the solubility, sometimes written, equals some constant times the vapor or the pressure above the system. Concentration could be molar. Because the constant doesn't change, you can also relate it this way, that the solubility at one pressure equals the solubility at a second pressure. We saw it like that. I don't think we're going to do any calculations with this, but we want to know this qualitatively. So the higher the pressure, the more soluble a gas is. What would happen if you opened a Coke at the bottom of the ocean? In theory, if it's a higher pressure, right, less splash should occur. More of it should just stay in there, right? Finally, Henry's law is really important for scuba divers, right? You think about something called the bends. It has to do with nitrogen in the nitrogen gas in your blood. And at lower pressure, so if you go down deep, the pressure is higher, so more N2 dissolves in your blood. As you come up, if you come up too fast, that N2 starts to become less soluble in your blood and starts to escape, right, and into your muscles and various other things. It's kind of painful. Oh no. Right. So they throw you in a hyperbaric chamber and you're okay. Also, Lake Nyos is kind of an interesting story where the solubility of a gas dissolved in a lake had catastrophic effects when the lake was kind of turned over. But that was temperature, pressure, and solubility of gases and solids. We'll take a look at some other ways to represent concentration next.